Hello and welcome back. In 2.6 we get to work with infinite sets. So first we'll work on the idea of one-to-one correspondence. So we're going to let set A contain elements P, Q, and R, and set B will contain elements 1, 2, and 3. I can pair P with 1, Q with 2, and R with 3. So every element of A was sent to a place in B, and everything in B had an element placed with it. So this is what we call a one-to-one correspondence. So an example where we don't have a one-to-one correspondence. I'll say set C is 1, 2, 3. Set D contains pi, E, I, and theta. This I would not be able to place a one-to-one correspondence. I can pair the 1 with the pi, the 2 with the E, the 3 with the I, but theta here does not have a partner, so this is something that is not one-to-one. Now, where that one-to-one correspondence comes in, it is a useful tool for figuring out if a set is infinite. So a set is infinite if it can be placed in a one-to-one correspondence with a proper subset of itself. And that is messy. So for example, a set of natural numbers, 1, 2, 3, 4, and the general term here would be n. I can make a proper subset by removing even just one element. So we'll call set A 2, 3, 4, 5. So then the general term here would be n plus 1. So our first term is 2, 1 plus 1 is 2. Second term, 2 plus 1 is 3. Third term, 3 plus 1 is 4, etc. And we can make that nice mapping. So 1 pairs with 2, 2 pairs with 3, 3 with 4, 4 with 5, and for the general term, n with n plus 1. So this shows that n, the set of natural numbers, is an infinite set. So we took the set itself, we created a proper subset of the set, and found this nice one-to-one correspondence, one-to-one mapping. Let's do a little bit of work with the general term. make E set of even natural numbers, 2, 4, 6, 8, 10. I'll leave a little room for our general term. So our lightly above just put which term it is. Our first term, I have a 2. Second term, I have a 4. Third term, I have a 6. Fourth term, I have an 8. Fifth term, I have a 10. See if you can figure out how to go from the red to the black, what you would do to the red to get to the black. And hopefully you recognize you would just multiply it by 2. So our general term here would be 2n. If I do multiples of 3, 3, 6, 9, 12, 15. Again, think of how you would get from the red to the black. So 1 sent us to 3, 2 sent us to 6, 3 sent us to 9, 4 to 12, 5 to 15. Each time we're multiplying our entry by, this time, 3. So that would be our general term. Now occasionally we're sort of shifted. So it's not necessarily always multiples of the distance apart. I'll just name this guy A, I guess. Let's say we have 8, 18, 28, 38, etc. I'll leave some room for our general term. There's 2 things to do with a list like this. One is to note the distance. Note these are all 10 apart. So there's going to be a 10n involved in it. But notice 10n by itself doesn't get us there. 10 times 1 would give us a 10, not an 8. 10 times 2 would give us a 20, not an 18. 10 times 3 gets us to 30, not to 28. But notice we're all the right distance away. We're all the same distance each time away from what we would expect to see if it was a nice, neat, pretty one like the last 2 examples. Each of these is just 2 under what we would get if we did the 10 times our entry number. So all we'll do is drop 2 off at each time. So for example, for our 4th entry, 10 times 4 is 40. 40 minus 2 is, there's our 38, and that's our 1, 2, 3, 4th entry. So distance between the consecutive entries, multiply that by your n, and then find the adjustment to get to the first element. So adjust to get first element. So for example, 10 times 1 is 10. Our first element was 8. That's 2 under that. So this next one we're going to do a couple things with. We're going to do set B. It's going to contain 3, 7, 11, 15, 19, 23. I'll leave some room for the general term. We have our ellipsis before and after the general term. So what I'm going to ask you to do is just pause it and find the general term first. Unpause it once you're done finding that. Okay, welcome back. So our distance between the entries, these are 4 apart, these are 4 apart, these are 4 apart, they are all 4 apart. So we know there's going to be a 4 times n involved, but 4 times 1 is 4. We see a 3 here. 3 is 1 less than what we had. So that should be your general term. The next thing we're going to do is we're going to prove that this is an infinite set. So when we're proving that, remember we form a subset, and not just any subset, it has to be a proper subset. So in other words, we're going to ditch one element. We'll name this guy C. Some label it as B prime, but that tends to get confused with the complement. So we'll just give it a different name. So this one, I typically just drop the first element. So 7, 11, 15, 19, 23, 27, and so on. And I have to leave room for my general term. So these are all still 4 apart. So I know there is a 4n involved. 4 times 1 is 4. I'm 3 higher than that. So I'll have to add 3 to get to my first element. And if you're not sure if it works, just pick a 2 or a 3 or a 4. 19 is our 4th element here. So 4 times 4 is 16. 16 plus 3, sure enough, is 19. So you can always test it out. You can always plug a number in and see, does it work? So here is our 1-to-1 mapping. So 3 goes to 7. 7 goes to the 11, and so on. And our general terms, 4n minus 1 goes to 4n plus 3. So we have shown that B is an infinite set. We have you all try one out. So you're going to show A is an infinite set, and our new A, so not this old A from this, let's just do 10, 20, 30, and I'll let you fill in the general term. And show that that's an infinite set. Okay, welcome back. So our general term here is just a 10n. We don't have to do any adjusting. They're all 10 apart, and 10 times 1 is 10, right on the money. So there's different things we could have done for our proper subset. The most common was probably to drop our first element. So this would be a 10n plus 10 for the general term. And we can make our mapping diagram that way. And that shows that A is an infinite set. We could have also done, say, multiples of 20. Multiples of 20 would all be in this set as well. So someone else might have picked a different set, but still gotten a nice, pretty one-to-one correspondence. 20, 40, 60. And those would be 20 n's. And we still would be able to use our arrows to get our one-to-one, and same conclusion, A is still a finite set. So the next thing we look at are countable sets. Set is countable if one of two conditions exist. It is finite, so it just comes to a nice, neat, pretty end. or it can be placed in a one-to-one correspondence with the set of natural numbers. And one more definition real quick. If a set is both infinite and countable, cardinality is referred to as Aleph null. A fun little letter there. So these would be considered countably infinite. So for example, let's work with the even numbers. Specifically even natural numbers, so 2, 4, 6, 8. Our general term 2n. So if we're going to show it's countably infinite, first we have to show that it is infinite, and then we show it is one-to-one with the natural numbers. So here's our general 2, 4, 6, 8 general term 2n. Then we go with our subset, proper subset. So for this one, we could do multiples of 4 or multiples of 8, or we can just drop the 2 from it. Let's do the... Okay, so we'll try out multiples of 4 for our proper subset. So 4, 8, 12, 16. So our general here would be a 4n, and that is a proper subset of set E. And we can make our one-to-one correspondence. So E is infinite. So then we'll check, okay, since it is infinite, can it be placed in a one-to-one correspondence with itself? We showed that it is not finite. It doesn't, number 1 doesn't hold. So a one-to-one correspondence with the natural numbers. Our naturals, 1, 2, 3, 4, and our general term n. And our evens E, 2, 4, 6, 8, general term 2n. And if we can make this a one-to-one correspondence, which we can, 1 goes to 2, 2 goes to 4, 3 to 6, 4 to 8, and to 2n. So we've made that one-to-one correspondence with the natural numbers. Therefore, E is countably infinite. Cardinality of Aleph null. All right, so some problems I would recommend from 2-6. I would try 1 to 3 all and 5 to 25 on the odds. If you have any questions, please get in touch. Otherwise, I will see you next time. Stay safe out there.